Good morning. Welcome to Turfgrass Epistemology. I'm TravisShaddox. I'm in a really good mood. We're going to have a good show today. We have a lot to get over, we have a lot to do to go over. And I want to get out of here in an hour because my voice is going to go. I have a sick daughter. I think I caught something from her. I don't know. Real quick, this is Turfgrass Epistemology. We're here searching to find out how we know what we know about turfgrass science. We're going to be going over some soil testing stuff today with potassium, some putting green ball roll, some quality. We have a USGA green section article we're going to talk about today. Phosphorus correlations. It's really more of a soil testing episode, but we're still going over potassium for this month. And this is a potassium episode. So look forward to all that. But I got to get going because otherwise this is going to be a very long episode. I changed the chat. I wasn't real happy with the way it looked, and I'm not real convinced I'm happy with the way it looks now. But just to understand, if you're chatting and you want to participate, that's great. I appreciate that. Just understand it might look a little different and it might be a little funky until I work out the kinks. I worked on it all weekend trying to figure out how to do this. And I, as you all know, I have no idea what I'm doing. Technological incompetence is my middle name. So I'm trying my best to, get this all worked out the way I'd like to see it. But there's some things that are going to be happening to the channel that include some chat options, but I couldn't do it the way it was set up. It was looking weird. So I adjusted that, and hopefully it's working. We'll see what happens today. But don't be surprised if you try to chat and something messes up or who knows what. Maybe who knows, but whatever. Okay, let's get into today because it's going to be long. I'm just being frank. You might as well just sit back and relax because we're going to be here for a while. Okay, when my voice starts to go at an hour, which is usually about when it starts to go, I guess I'll start speeding things up and who knows what. But we'll see how long we go. But good morning, Andrew Burris. Oh, congrats on the 900 subs. Oh, yeah. Let's look and see how many subs I got. Let's look here. It says 911. Okay. So we're getting somewhere. Slowly but surely. I started with 0. So when the first 2 or 3 shows I did with 0 people. And it's building. So we're getting there. Vahid Navi, hello, good morning. Lush, Wayne, good morning. Super TA, Connecticut Kubonican, good morning. Brady, everybody's here. Rich the Long Guy, Randy from Bulgaria. DST already. What does that mean, Randy? I'm sorry. I'm not really savvy with all the acronyms. Yeah, I don't know what DST means. Sorry. Okay. Now let's get to it. So we have a really good article. I mean, the article has a few little quirks in it, but the article is very, very good. Today it has a lot of really good information in it. Oh, daylight savings times. Thanks, Randy. Yeah, it is. Unfortunately, I don't know why we do that in the United States, but some of the other countries follow along. In Brazil, they do it as well. But when they go forward, we go back, and we go back, they go forward. So, any time of the day or any time of the year, we're either 1 hour ahead of Brazil or 3 hours ahead of Brazil, depending on it. Because when we go forward, they go back, and we move 2 hours. So anyway, make a long story short, my family in Brazil, sometimes we got to remember they're 3 hours or 1 hour because of daylight savings time. Okay. But so potassium, we're going to be going over that today. And it's a really good article. It has some really good information in it. And somehow, I guess in my preparation for this potassium week or whatever, I don't know really how, maybe just coincidental, I came across a USGA green section article that I wanted to go over, and today might as well do it today because this episode is going to have, or this article has some soil sampling information in it, depth and changes throughout the season. And I thought it would be relevant to, or the USGA article would be relevant to today's scientific article. And so let's get into it. The article that I want to talk about is called The Importance of Year-Round Soil Nutrient Analysis which was just published in the USGA Green Section Record on March 1 of this year, 2024. And it's March 11th now. And it's by Chris Neff. I've ran across Chris over the years when I was in the sales. He was a superintendent over in Florida for a while. And he wrote this article. And I want to go over this article, or just a couple pieces of the article, not the whole thing. The article itself is, the majority of it's okay. It's not particularly, troublesome, but there's a couple things in there that are curious. And the USGA Green Section has published, they're well known for being very reputable, very respectable in terms of their content that they put out over the years. But in the last 2 or 3 years, they put out some real clunkers. They put out an article 3 or 4 years ago, I don't remember exactly when, about the importance of using base saturation as an interpretation for soil tests, which is completely flawed. False and flawed at the same time, flaws. It's completely flawed. I don't know where they got that information from, but they actually ended up pulling that article. It was published, and then to their credit, they actually removed it. I don't know where they got that information from or why they published that, but it was horrible. And then they published an article a year or two ago. I don't remember when it was done. I can't remember the exact topic now. It had to do something with sodium or salts. I can't remember exactly what it was. But there was a lot of very questionable information in that article. I mean, I don't know who's editing these articles, or I don't know if anybody's editing these articles, but I don't think they have a soil scientist on staff, because they put out some stuff nowadays that is just bizarre. I'm not sure exactly who's writing it and who's editing it, and I don't know. And this is one of those articles. There's some information in here that I have to question as a soil scientist. Do they even have a soil scientist at all looking at this stuff before it actually goes out? I don't think so. I know they have a really good water scientist. I mean, top of his class. I mean, top of the world probably in terms of water science and water usage and stuff. But when it comes to soil science and nutrients and things like this, soil testing, maybe I'm wrong, but I don't know who they have on staff there reviewing these things. But anyway, let's get into it. The article, like I said, is called "The Importance of Year-Round Soil Nutrient Analysis." And the first paragraph is really all I want to talk about, maybe a little the second paragraph. But Chris says, after a colder than average winter in the southeast, it is safe to say that most in the golf course maintenance industry eagerly anticipate warmer temperatures and the emergence of turf from its dormant or slow-growing stage. One common trend observed during my travels so far in 2024 is preparing for the upcoming spring golf season by applying fertilizer. To adequately make decisions regarding these crucial fertilizer applications, it is imperative to conduct soil sampling throughout the year to assess soil properties and current nutrient levels, which play a vital or pivotal role in the overall health and performance of the course. To ensure optimal results, it is recommended that sampling be conducted at least 3 times annually. Here are just a few reasons why year-round soil sampling is a good idea. And he gives some reasons, and none of them are particularly valid or compelling at all. But I want to talk about 2 things in that paragraph. To say it's imperative to conduct soil sampling throughout the year, not just once a year or once every 2 or 3 years, which even then, to say it's imperative to soil sample every 2 or 3 years is a stretch. But he's saying it's imperative to conduct soil sampling throughout the year, more than once a year. And he says it's recommended sampling be conducted at least 3 times a year. 3 times each year. This is coming from the USGA Green Section Record. Okay? I don't know where he's getting this information, but I seriously doubt he's getting it from any reputable soil scientist. I'm not familiar with any reputable soil scientist that would recommend sampling 3 times a year and make it imperative that that's done. I'm not aware of anybody. And not that that necessarily is a reason to not do it. I'm just saying that the people who do know and the knowledgeable experts in this area, I don't know of one that would recommend that, because there's not a lot of evidence to support that. And there's some evidence to refute it, which is actually what I'm going to go into in a minute. So he has 3 reasons here: monitoring nutrient levels and imbalances, assessing nutrient uptake, and enhancing environmental and economic sustainability. Okay, so let's go into each one of these individually just for a brief moment. Monitoring nutrient levels and imbalances. The only reason that I can think of that would be an evidence-based approach to monitor nutrient levels would be if you've had a pre-existing condition, a pre-existing nutrient deficiency, and you wanted to monitor that to make sure that let's say you've had a problem in the past, and your turfgrass was unacceptable in the past because of a nutrient deficiency, and you wanted to, you've alleviated that. You applied phosphorus or whatever the case is, and you alleviated that deficiency, and you wanted to make sure that your nutrient levels were at an adequate level moving forward so you wouldn't experience that deficiency again, which is not a great reason, but it's okay. I'll go with that. That would be okay. Okay, that would be a reason to monitor nutrient levels. If you've had a pre-existing deficiency, a pre-existing unacceptable turf, you've diagnosed it, you cured it, and you just wanted to maintain that over time, you wanted to make sure your nutrient levels were greater than that previous pre-existing level. Okay, no problem. But that's not really what he's going at here. Very few people I'm aware of would actually argue, besides me, would argue that soil testing is valid to diagnose issues or to determine, to maintain levels that were known under pre-existing condition issues levels. Okay, pre-existing issues is generally maybe not worded that way, but it's not generally that's probably. There are probably some people that do that. So that's I'll back up. There's probably some people that do soil test because they've had a pre-existing condition. It's not that common, but it probably happens. I'll take that back. Okay. But then he uses imbalances. I don't know what Chris means when he says imbalances, but he's treading on thin ice on that one. Okay. Nutrient balances. Okay. When you start using nutrient balances and the term nutrient imbalances, you start moving into the base saturation worlds and the calcium magnesium balance world, which is complete, it's nonsense. Okay. It's a grift. People use that in knowing it doesn't work to sell fertilizer. Okay. So be careful when you start using that term. But then he says assessing nutrient uptake. Okay. The next one is assessing nutrient uptake. And he talks about various things and, pH and rainfall and soil minerals and things like that. Effective availability. I'm not going to nitpick on that one. Just as a soil test isn't really going to assess the nutrient uptake per se. Okay. You're not going to be able to determine how much was taken up into the plant by measuring what was in the soil. Okay. There's all sorts of fates of nutrients. One of them is plant uptake. But I don't know how you would be able to with any confidence, determine how much got into the plant by measuring what was in the soil. And that goes for a number of nutrients, but whatever. Then it says enhancing environmental and economic sustainability. That is a huge assumption. What he's saying is regular 3 times a year soil sampling on golf courses would enhance the environmental and economic sustainability of the course. Okay? It says specifically, year-round soil sampling with aligns with environmental and economic sustainability principles. Okay? By assessing the nutrient status of the soil, golf courses can optimize fertilizer applications and minimize the risk of nutrient runoff. Providing the correct amount of nutrients in each application demonstrates environmental stewardship, prudent financial management, and results in better conditions throughout the year. There is one other. Let me back up. There's an issue with that. But then up here he says, this ensures that the turfgrass effectively utilizes nutrients and that fertilizers are only applied in the necessary amounts. So year-round soil sampling 3 times a year ensures that turfgrass effectively utilizes nutrients. I have no idea how he's measuring that. And that fertilizers are only applied in the necessary amounts. So every nutrient that goes out, according to this argument, would be put out in only the necessary amounts of fertilizer. So there's no waste. There's no excessive amounts of phosphorus, no excessive amounts of potassium, and any other nutrient, because you're doing 3 times a year soil sampling. That's his argument. These are horrible arguments. They're not supported by evidence. The third one is clearly refuted by evidence. Okay? So let's look at that. So all you have to do is go to this article, which I don't know if I've actually covered on this channel or not. I don't remember. I know I talked about it on another podcast, but I don't really remember if I did it on my own podcast. This is called Nutrient Use and Management Practices on United States Golf Courses. That was published by Shaddox, Unruh, Johnson, Brown, and Stacy. We published this a few years ago in Hort Technology. And we surveyed the nutrient usage on golf courses. And in here, we included prior questions about soil testing. We also added some new questions about soil testing because I wanted to know more about what is actually going on and is there a relationship between various practices and so forth. So in here, and if I haven't gone over this, I'll go over it at some point in more detail. But for today's purposes, when Chris is saying economic and environmental stewardship, basically you'll enhance environmental stewardship and enhance your economic, basically be better with your budget. That's not supported by evidence at all. I wanted to show that. In here, on table 10 and table 13, I'll go into this article in more detail later, but basically this article is looking at all the U.S. golf courses, and we wanted to know, basically nitrogen, phosphorus, potassium applications, what's common, what's not common, how you do it. And in here on table 10 is the frequency of soil extract used for analysis of phosphorus and non-phosphorus nutrients. Now, before this publication, as far as I'm aware, there had never been any data on the prevalence or usage of various soil tests on U.S. golf courses, at least a national survey. We didn't know. We had no idea, nationally what golf courses are using, what sort of soil extract are the people actually using. And this is broken out by regions, North Central, Northeast, Pacific, and Southeast, all these things. And then it has the overall U.S. average. And the extractants the options are saturated paste, Malic 3, Bray, Malic 1, Olson, and a modified Morgan extract. And in the United States, 47% of golf facilities reported they used saturated paste for phosphorus analysis. Phosphorus analysis, saturated paste. Now, I haven't gone into a whole lot of I don't think I've gone into any detail on soil testing yet. But saturated paste is not an evidence-based approach for phosphorus analysis. It's useful for salinity, it's useful for pH, okay, but not for phosphorus. And yet we have half of the golf courses in the United States reporting that they use it for phosphorus analysis. So if half are using an invalid extractant, why should they be sampling 3 times a year if they're sampling extractant is not an evidence-based extractant? They're not even using the correct extractant, right? 23% are using Malic 3, and all these other ones are valid, Bray and Malic. All these are depending on where you live and what location you're in and so forth, what type of soil you have and so forth. These are all valid extracts. But saturated paste is not an extract that's an evidence-based extract for phosphorus on turf grasses. So it should be none. They shouldn't be soil testing at all if that's what they're using. If they're using saturated paste to determine phosphorus and then apply phosphorus, there should be zero sampling, basically. That's what that says. All right. But yet we have the USGA green section saying you should sample 3 times a year. So that's a problem, that they're not even using the correct extract. But let's make the case even stronger. If you go down to table 13, which is also a new table, these questions had not been asked in the past. or not asked in this particular way, or sorry, not analyzed in this particular way. Table 13 shows the association between management practices used with the intent of reducing reliance on applied nutrients. So the question, that's exactly how the question was worded on the survey. Do you engage in this management practice with the intent of reducing reliance on applied nutrients? And the options were, do you fertilize based on soil test results? Do you return clippings? Do you use precision fertilizer applications? And you can read down the whole list. Okay. The only management practice on this list, and these are things including stop overseeding, compost on site, change turf cultivar, use new fertilizer guidelines, reduce overseeding, all these things, use plant growth models, all these things. The only option that resulted in an increase in nutrients on nitrogen, phosphorus, and potassium was if you fertilize based on soil test results. It's the only one. There's other ones on here that result in what you would hope we would result in. We result in less usage. Like, for example, if you return clippings, you result in less phosphorus usage. If you use precision fertilizer application, there's an association between that and using less phosphorus, and so forth. Okay, so there's other options. These are risk factors, basically. And there is some association between some of these risk factors and a reduction in phosphorus usage, right? Reduced turf acres, there's a reduction of phosphorus usage, and there's a reduction in potassium usage as well. But the risk factor associated with increases in nitrogen, increases in phosphorus, and increases in potassium was fertilizing based on soil test results. So, if you're going to make an argument that you should sample not only once a year, you should sample 3 times a year because it enhances environmental and economic sustainability, I'm not buying it. Because I haven't seen any evidence to support it, and here's evidence staring us right in the face, refuting it. Okay? If you fertilize based on soil test results, you used approximately 1.5 more tons of nitrogen per year than if you didn't. You used nearly twice as much potassium. You went from 1.7 tons per year to a little over 3 tons of potassium per year. This is for an 18-hole golf course, I believe. This is how I analyzed that, I think. 18-hole equivalent, I believe. So you're almost doubling the potassium if you soil test. You're almost doubling the nitrogen if you soil test. And the phosphorus goes from 0.3 tons to 0.6 tons. So you are doubling the phosphorus if you soil test. So the only question is, are all those extra nutrients actually needed by the turfgrass? Right? We're unable to answer that question. We don't know. The likelihood is very low because that would mean that every golf course that's not sampling would have unacceptable turfgrass. If you're not soil sampling, then you would fit into was the management practice used no category, right? And if you're not soil sampling, then your turf would be unacceptable. And if you are soil sampling, you're applying these nutrients and your turf is acceptable, then that'd be a good argument to continue to apply these these nutrients, these needed nutrients in that case. But as we're going to talk about today with this potassium column right here, we're going from 1.7 tons to 3 tons per course per year with potassium. And we found the last couple articles, we're going to find again today, and the remaining articles basically, that there's really no value to applying all of that potassium. There is value occasionally to applying some potassium at some times of the year on some turf grasses. That's true. But applying these excessive rates of potassium are not warranted in almost every case. Okay. So if I can just briefly go back to the article, if I can get there, is, let's see here. If I can do this. I don't know if I can do this. I got so much stuff going on here. Is this article is highly questionable. I don't know where they're getting it from, and I suspect there's not as soil scientists reviewing or editing this content before they go out. Because it's not imperative, don't believe that, it is not imperative to conduct soil sampling 3 times a year. By any stretch of the imagination, that's not imperative. Most courses that I know do perfectly fine sampling, say 6 greens 1 year, and then they just rotate. So they're sampling the same green every 3 years or so, the same fairway every 3 years. And they just rotate the other 6 and so forth. So they're doing all 18 holes on a 3-year cycle. Okay. And they're fine. Doing it 3 times a year is absolutely absurd. Okay. I don't see any evidence to support that, and there's no reason why you should believe it or do it. Okay. So that's that on the USGA green section. Oh, by the way, I just got, right before I got on here, I was looking at reading this article, and a recommendation popped up on YouTube to go over and look at Asian Turfgrass website or YouTube or whatever. And Dr. Woods he actually discusses this article as well, a little bit of it. And if you go over there and look at the Asian Turfgrass Center YouTube, which I encourage you to do, he starts talking about it about 16 minutes into his video. He talks about it for about 5 or 10 minutes. He's much more politically correct than I am. He's much softer in his language. So if you want a different take on it, feel free to go over and listen to Dr. Woods. He has it's a similar take as I have. He's just more PC about it. So, okay. Let me see. Now let me get my bearings here. Okay, I'm sorry. I'm just trying to get all this stuff where I need to put it here. Okay, so what I want to do now is I want to go to the article, and before I go, before I start reading the article, let me read the chat here. So it looks like the chat is actually working. Brent says that's a lot of tests. Yeah, that's a lot of tests. That is a lot of tests. And then Randy says soil testing made by fertilizer company ? Interpretations made from them ? You know, I don't really know. I doubt the interpretations made by the fertilizer company. Unless they're, I guess it's possible, but most fertilizer companies don't have a soil scientist on staff to make a valid recommendation. I know they exist. There's 1 or 2 out there, but I suspect they're probably using their interpretation from the lab, but that doesn't help because the lab's interpretation is usually much higher than what we find when we do proper correlations in the case of fertilizer applications, calibrations, to know how much we need to apply. And I have yet to even find a case where the soil lab interpretation was equivalent to what we find in turf. It's almost always higher. I've yet to find a case where it's equal or lower than the turfgrass, the proper correlated and calibrated turfgrass interpretation, unless they've already done it on the turfgrass. That's different, but they're almost always higher. The potassiums will be like in the 80s and 90s parts per million. That's when you need to apply it on a soil test usually, and that's usually far higher than you ever need. Phosphorus sometimes is in the 60s and 70s or even higher on some soil test interpretations, and that is many, many magnitudes higher than what turfgrass actually requires. Magnesium is another one. Magnesium is quite low usually on on turfgrass needs. There's usually quite low, but soil test interpretations will be, 80, 90 parts per million, usually higher even. Okay. So I don't really have any confidence on a soil test interpretation. In the old days, like in the 90s, in the early 2000s, I gave many talks on saying, don't worry so much about the actual number. If you don't know how to interpret it, just go by the interpretation on the soil test. And that was in collaboration or in counseling with a soil scientist who's very respected. And I respect his opinion on that, but his opinion is based upon tests that are properly correlated and calibrated. And if you're getting it from any soil testing lab, there's no way to know for sure whether or not it's calibrated unless you talk to a scientist or talk to someone who did it at the lab. Okay, so many of the university tests don't have the proper correlation or calibration done on turf grasses, but some of them do. But I don't know of one independent commercial lab that is actually using properly calibrated values to provide their interpretation or to produce their interpretation. I don't know of one. Doesn't mean they don't exist. It could exist, but I don't believe their interpretation is accurate unless I actually see what calibration curve they're using to provide that recommendation. Okay. So, and to be frank, nowadays, if you just know the literature somewhat, I know I haven't gone into the soil testing literature that much. I understand that, but I'll go into it a little bit today with potassium and a little bit with phosphorus with this particular location and grass. But the numbers are in there in the literature. I mean, you can't find one for every turf in every situation. I mean, that's never going to happen. But you can be pretty confident if you just have some, foundational knowledge of the literature that, you should kind of have a ballpark idea. Perfect example is sulfur. When I was diagnosed that 2, 3, 4 years ago, whenever it was, I was running into a lot of sulfur problems, and we don't have any sulfur correlation or calibration as far as I know in turfgrass management, particularly with Malic 3, we don't have that. And so I went to the literature and looked up agricultural crops. And if the agricultural crop, if the value if the agricultural crop value in my case, I knew it was somewhere around 10 for sulfate deficiencies, and say, I forget what the paper was I was reading, but they found it somewhere around 10, 9, 10, 11, something like that. And my value at the time was 5. So I could have been still fine because turfgrass generally doesn't need that much nutrients as compared to row crops. I could have been fine. But being half the value of agriculture literature, I felt like it's a possibility that sulfur could be deficient. And that's when I went out and did the study and found out, in fact, it was deficient. Okay, so if your value is greater than the soil test interpretation, chances are you have more than enough. If it's lower, you don't know, because you don't know if it was conducted on a turfgrass calibration curve or not. Anyway, sorry about that. I'm getting into soil testing too much. But okay, let's get into this article. Nitrogen, the title of this is Nitrogen, Phosphorus, and Potassium Responses and Requirements in Calcareous Sand Greens by Johnson. I never know how to pronounce this name. Koenig? He's been around. I've seen a couple articles with him or her on it. And then Kelly Kopp. This was published in Agronomy Journal in 2003. So you can go there and read the abstract if you can't get the article. This is a pretty good article. Okay, this is actually a really good article. Like I said, there's a couple little quirks in it that are a little bit like, man, I wish they would have done that and done this, but it's fine. It's a good article. So the authors say plants growing on calcareous media commonly exhibit phosphorus and micronutrient deficiencies because the alkaline pH of these soils renders these nutrients unavailable. Nutrient problems are magnified when calcareous sands are used as the primary ingredient in sand root zones. Due to these nutritional problems, turfgrass managers often have difficulty growing satisfactory turf on calcareous sands. I suppose that's true. We're going to find out in this article that they didn't find any evidence to support this difference, but it's possible. Let's see here. Our objectives were to determine the effects of nitrogen, phosphorus, and potassium, and the interactions of N and K and P and K on the growth of creeping bentgrass on calcareous sands in the Intermountain West. So we're going to be in Utah for this, guys and gals. We used turf quality ratings and soil test measurements, but also included tissue tests and determinations of ball roll. So we're going to talk about ball roll and all sorts of fun stuff today. This study was conducted, the research putting green constructed in 1995 to a modified USGA specification in North Logan, Utah. So we've gone over a lot of different articles, and I don't remember one being in Utah. So for any of the Mountain West folks who might feel like you're getting neglected by all the stuff I go over, here's one for you guys in Utah. The sand used in the green differed from USGA specifications by having a greater percentage of fine sand. So it was a smaller particle size for this particular setup, with 23% of the mix in the 0.15 to 25 millimeter particle size range and 12% of the mix being in a smaller particle size range. The root zone mix was specified as 95% calcareous sand and 5% peat to a depth approximately 12 inches. The actual mix was tested in 1998 and contained 95% sand, 3% silt, 2% clay, and 0.5% organic matter. I'll go over that. The putting green turf consisted of a Providence creeping bentgrass. Initial soil test using a 0.5 molar sodium bicarbonate. So this is going to be an Olsen test. So I know the Olsens and the Brays and those people using them sometimes don't get all the love. They feel left out because we always talk about Malix and all these things. And that's, that's reality. But in this case, we're talking about the Olsen extract, the sodium bicarbonate extract, which indicated low phosphorus and potassium levels. Okay. And I'll show all the levels in just a second. In general, the turfgrass quality of the putting green was relatively poor and would not have been acceptable for a typical golf course at the time these studies were initiated, primarily because of poor density and a lack of growth. Okay. So they started off, which is the way you don't always have to start off this way, but if you're looking at nutrient response work, you need to start off with turf that is not perfect. That's the reality. If you start off with the 10 or 9 on the quality scale, which is the top of the scale, you can't go up from 9. So you need to have a turfgrass that is at least marginally acceptable in order to see a response, because perhaps the unacceptable turfgrass is a result of a nutrient deficiency. So they started off, in my opinion, in a good location. 2 separate but related experiments were initiated in April of 1999 and continued through September 2001. In Experiment 1, phosphorus and potassium rates were varied, while nitrogen was held constant. Experiment 2 involved varying rates of nitrogen, and potassium was held constant. Varied rates of N and K, with phosphorus being constant. I apologize. In 1999, the fertilizer treatments were divided among 6 applications between October and November. Now, remember this. The first year, they applied the nutrients 6 times throughout the year between April and November. And then the next year, they applied it monthly, 12 times a year. And it's not that important, but I'm going to show you a graph at the end that you have to come back and remember that. Okay. Some burning of the turf was observed due to the high rates and high salt content of the fertilizer solution. In 2000 and 2001, the same yearly nutrient amounts were divided above 12 applications. They applied them as liquids to the turfgrass. We're on a putting green, don't forget. Visual ratings of turfgrass were 1 to 9, but they don't say in here what the minimum acceptable limit was. Sometimes it's 5, sometimes it's 6, sometimes on putting greens they say 7. So I don't know exactly where it is, and I've read this. I can't seem to find what the minimum acceptable limit is. They do talk about minimum acceptable turfgrass, but they don't provide the value they used. So I don't really know what to say about that. So anyway, the soil samples from each plot were collected 5 times each year using a probe to extract a core of 6 inches. And the soil test phosphorus and potassium were measured using the Olsen test. In year 3, a separate test was conducted on a selected plots in both experiments to measure the soil test potassium at depths within the soil profile down to the gravel drainage layer. All replicates of the plots receiving the highest and lowest rate combinations of phosphorus and potassium experiment 1 and nitrogen and potassium experiment 2 were sampled using a soil probe. The core was divided into sections. So basically they're going to look at the soil in 0 to 3 inches, 3 to 6, 6 to 9, and 9 to 12 inches in depth. So they're going to look at the nutrient extract based upon the depth that the soil was taken from. Okay. And so that's it on the materials and methods. So basically, the short and skinny of it is they're on a calcareous putting green on Bentgrass in Utah. They're going to look at potassium rates and nitrogen rates and a little bit of phosphorus. They're going to do some soil testing. They're going to do some tissue testing. And they're going to attempt to determine how much potassium is needed, how much phosphorus was needed, was there a response to either one of these, nitrogen was needed, and so forth. And they're going to sample the depth of the soil to determine at different depths what the changes in nutrient. Well, they're only going to show potassium, but the changes in nutrients were at depth. Okay. And they're also going to do it over seasons, over months. So they're going to sample 4 times throughout each year. So you're going to see April, May, June, it's April, June, August or something, which is going to be critical to the USGA paper that I just talked about. Okay. Because they're going to show the changes in the soil test nutrient level over the years. Because let's look at the chemical properties and the physical properties of the root zone itself. So the pH was a 7.7. Salinity was low, 0.2. Anything below like 2 is probably fine. Anything around above 2 to 4, you start being worried about salinity. They're at 0.2. Organic matter was low. Look at the phosphorus. Well, I don't even know which one this is. The phosphorus was 2.5. Potassium was 16. Okay, so the phosphorus is quite low, 2.5. This is, don't forget the Olsen extract, but it's still low for that. And the potassium was 16. Okay. CEC was 1 and the sulfate was 2. They talked about they applied some sulfate up here. They said extractable zinc sulfates were low, and they amended the low sulfate levels with sulfur. They amended. They knew the sulfate was low, and they applied some sulfur to alleviate that deficiency across all the plots to eliminate that as a variable. Okay, so that's the soil. That's the setup. Okay, now let's get into the results. I'm going to show two of the results in a graph. I just think it'd be easier to see it that way. Okay. Creeping bentgrass turf responded to phosphorus. So listen up here, okay, guys and gals, okay? If you're in your truck, you're in your shop, you have me on the radio, whatever it is, you're out working, just listen up real quick, okay? There's a lot of good results here, but I want to highlight a couple of them so you really don't miss this. Creeping bentgrass turf responded to phosphorus treatments soon after the experiment began. Before the experiment, the turf was lacking density and leaves exhibited characteristic purple deficiency symptoms. I keep getting emails, and that's fine. Keep sending me emails. And I'm sorry I can't respond to everybody, but often people are asking about phosphorus deficiencies and what to look for and all these things. It's usually a reduction in clipping yields, growth. It's not growing quite as fast, and it's a little off color in terms of purple. It's purplish, but sometimes it can kind of look a little grayish. Just depending on how your angle and what you're looking at in terms of where the sun is to where you are looking at it. But anyway, it's generally a little purplish, a little darker color grass, and it's usually not growing as fast. That's telltale signs of phosphorus deficiencies. And what they said in the very first sentence, which is what I want people to understand, is that creeping bentgrass turf responded soon after. It doesn't take months to alleviate a phosphorus deficiency. It's usually very rapid, within a week or two, probably within a few days. But they say specifically, soon after the experiment began, the phosphorus treatments popped out. You could see them. Okay, so don't lose your cool and lose your sleep because you saw some purple turf out there. It can very easily be resolved. It's not a problem. And you don't need to go out there and throw in copious amounts of phosphorus out there because you think you're losing the farm and you're going to lose your job. Just apply a little bit of phosphorus and they'll come back. No problem. Okay, it's not the end of the world. Plots receiving 0.1 pounds of phosphorus had significantly reduced turf quality, 3 out of 9, and were deficient as evidenced by the purple leaf discoloration. So 0.1 pounds of phosphorus was not enough. Okay. The remainder of the phosphorus treatments produced statistically similar results, ranging from 5 to 5.5 on the turf quality scale. The remaining amounts were right here, okay, where we see phosphorus, and they're all, I'll just read the phosphorus rates they use. They use 0.1 pounds, half a pound, 1 pound, and a little over 2 pounds of phosphorus. Those were the rates that they used. So whether you used a half a pound or whether you used 2 pounds of phosphorus, it was statistically the same. So just go out with a half pound of P. That's it. Not a huge issue. Okay. Pretty straightforward. The potassium rates, just while we're here, the potassium rates they used were 240. Well, they used 0, no potassium. But then they used 2, 4, 6, or 8 pounds of potassium per year. Okay. We're going to talk about that. And they used potassium chloride. Look at that. Okay. That's what you need to apply if you're going to be looking at potassium, because if they use potassium sulfate, if they did not see a response with potassium sulfate, then I'd be convinced that potassium didn't show anything. But if they did see a response with potassium sulfate, I can't say for sure it was from the potassium because it came along with sulfate. Turfgrass will respond to sulfate in some cases, but not to chloride. Okay. So those are the rates. And they said phosphorus was deficient. The turf did not look well at all. And the 0.1 pounds of phosphorus did not alleviate it. It was the 0.5 or higher that alleviated the phosphorus deficiency. Okay. Phosphorus fertilization increased soil and tissue phosphorus. Soil and tissue phosphorus were also related to turfgrass quality. According to the linear plateau regression analysis, soil test levels beyond 3 parts per million and tissue levels greater than 0.4% did not result in any increased turfgrass quality. Let's look at these graphs, Figure 2 and Figure 3. So Figure 2 is right here. Now remember, this is Olsen. Okay, it's not Mehlich 3, so Mehlich 3 is going to be a little bit higher. It's going to extract a little bit more phosphorus usually. But on this graph we're looking at is soil test phosphorus on the x-axis and the mean turfgrass quality on the y-axis. And this was the data are combined over all 3 years of the study. And we see the linear plateau peak at about, like he said, about 3 parts per million, somewhere right in here. Okay, guys and gals? So and you'll see this in the Kreuzer paper when I get over to the Kreuzer paper as well. You'll see very similar graphs to this, where at very, very, very low levels of phosphorus, we see unacceptable turfgrass. We're talking 1 part per million, 2 part per million of Olsen. We apply a little phosphorus, the phosphorus goes up, and about 3 or 4 parts per million is where we see the maximum turfgrass quality achieved. And this plateau is where we continue to see the phosphorus in the soil go up, but the turfgrass quality does not go up concomitantly. You're going to see this. It's going to change, from when we're going to use Mehlich 3, it's going to be out here closer to like 8 or 9. It's going to be somewhere out in here on the Kreuzer papers. But it's going to see the graph is going to look the exact same. It's just the scale is going to move up a little bit because Mehlich 3 is going to extract a little bit more than Olsen for phosphorus. But the point is that it's very, very low. The phosphorus level that is required to maximize turfgrass quality in this paper was around 3 parts per million Olsen phosphorus. So if you're on Bentgrass on a calcareous green, there's an extremely good, you should have very good confidence that if your Olsen extract says 4, 5, 6, you're right on that line. You're next to the cliff, okay? So you're floating around this little cliff here, right? And, I don't know how close you want to be to that cliff because you come over here and all of a sudden, boop, it drops off. So your willingness to accept the risk is up to you. Like I've said before, when I'm hiking with my daughter, she walks on the other side of me. She doesn't walk on the cliff side of me because she always wants to look over that cliff. She's like, Daddy, I want to look over that cliff. I want to go over and look at the edge. I'm like, no, you're not. I don't want her anywhere near that cliff because the risk is far greater than the reward. The reward is she gets a better view of the open Kentucky landscape, which is beautiful. The risk is she slips and she falls, God forbid. So I don't want to be near this cliff. How close you want to be next to that cliff in terms of phosphorus in your turfgrass is up to you. Okay. But clearly, if you're up here in the Olsens and you're on Bentgrass and you're up here in 15, 20 parts per million, or greater, there is very little evidence to support continuing to apply phosphorus. In other words, you're not going to see any additional increase in quality. There's not much reason to continue to apply it. Okay? And whether you like it or whether you don't like it, particularly with phosphorus, we're going to have to comply at some point because the evidence is becoming overwhelming that when you reach the critical level, you do not need to continue to apply more, and continuing to apply more is only costing you more money and increasing the potential environmental risk. And we just can't do that forever. Recognize and have confidence that the research has been done, and on creeping bentgrass in Utah on a calcareous green on an Olsen extract, if you're anywhere in the double digits, say 10 or greater, you're probably just fine. Okay? You're not going to see much benefit from adding more and more phosphorus. Now let's go to the figure 4, which is the tissue. Did I want to show that? Oh, I can show this. This is the tissue K. I'm not real big on this, but they have a line here, and I just want to point this out. They talk about, oh, wait, no, this is tissue. That's tissue K. I want to talk about tissue P. Oh, here's tissue P. Here's a similar line where we see he said 0.4, the author said 0.4, anything greater than 0.4, they don't see any further increase in turfgrass quality, which is what they found here. But keep in mind, they didn't publish the R square on this, or maybe they did and I missed it in the text. I don't see the R squared on this particular graph. But there's a lot of variability in tissue phosphorus in the turfgrass quality. There's a lot of variability. So I wouldn't, in other words, you could have 0.4 and see the range is like this. So this is what I'm doing is I'm circling all the dots. So the range is anywhere in the red circle between, say 3 on a turfgrass quality scale if you're at 0.4 phosphorus, or a 7 on the quality scale if you're at 0.4 turfgrass phosphorus. In other words, our confidence that you would see acceptable turfgrass if you have 0.4 phosphorus is not that great. I imagine the R squared on this is below 0.5. I don't know. I have no idea, but I imagine it's fairly low. Okay. So soil tissue tests, I've said before, I'll say it again, is that they're not that reliable. There's a lot of variation in tissue testing. I mean, it's crazy. So if you follow this and you say, well, I have 0.4, the paper said 0.4, I have 0.4, I'm probably fine. Well, this shows right here that all of these values right here below, at 0.4, are below the, I guess I'm going to say 5 is acceptable. They didn't say what the acceptable limit was, so I don't know what the acceptable limit was. But they're all below 5 on the quality scale. So, and there's a lot down into the 3s, right? There's some up into the 7s, but we just wouldn't know. We wouldn't have a lot of confidence in that, is the point. So let's continue. Okay. So, went through that. Ball roll. Ball roll was negatively correlated with soil test phosphorus, meaning that the more soil test phosphorus went up, the ball roll went down. Okay. The lowest phosphorus application, that was soil test phosphorus. The lowest phosphorus application rate, which was 0.1 pounds, resulted in significantly longer ball roll compared with the higher phosphorus rates. This was due to the relatively thin stand of the turf. So in other words, there was such little phosphorus, there wasn't much turf grass, and the ball was rolling farther. This sounds good. A ball rolls farther, but the turf grass was unacceptable, so it wouldn't count. It wouldn't matter. All right. Okay. This work indicates that relatively low levels of soil phosphorus are needed by creeping bentgrass. Previous levels greater than 7 to 12 parts per million Olsen were recommended. These data show that phosphorus levels can be kept very low, possibly discouraging annual bluegrass. Well, that's another issue, and reducing phosphorus pollution concerns. So there's another paper that I'll go over that talks about trying to tweak the phosphorus levels to favor annual bluegrass or creeping bentgrass. Well, you'd want to favor creeping bentgrass in most cases. So you want to keep the phosphorus levels a little higher. Phosphorus levels a little lower is where bluegrass doesn't do as well. And there's a really good paper on that I'll go over. But therein lies the issue, is that you don't want to rely upon a single phosphorus number. 20 parts per million, omega-3 phosphorus is the number for all turf grasses and all soil. That's absurd. Okay, and one reason for that is depends on which turf you're growing. If you're trying to grow POA greens, you could grow it with you'd want to stay a little higher. If you're trying to grow bentgrass greens, you might go a little lower. And if you have a competition between the two, then you need to be aware of that and adjust your phosphorus levels to enhance the chances of you growing creeping bentgrass over POA on your putting greens. Okay. So there's a lot more to it than just there's one number and you got to stay above that number. Let's go to nitrogen. Nitrogen is the nutrient that guides most putting green fertilizations. The 2 pound of nitrogen rate did not produce acceptable turfgrass quality. Figure 5, which is right here. You basically see 2 pounds. It was 2 pounds and then 1.5 pounds, and I can't remember the rates, 5 pounds and 7 pounds. I can't remember now. I can't do it off the top of my head. But anyway, you see the increasing nitrogen rates, you see increased turfgrass quality. It's not complicated. That's very common. But the lowest the lowest nitrogen application rate was 2 pounds, and it did not result in acceptable quality. Okay, let me just do that. I always forget these rates in my head. I think that's 3 pounds. 147 is 3 pounds. Is that right? Yeah, 3 pounds. And then 244 is 5 pounds. Okay, so 1, 3, 5, and 7 pounds is what they applied. They say that the 3 pound nitrogen application rate was a marginal quality, while the 5 pounds and the 7 pounds rates were ranked. Best in turf quality. So they needed about 5 pounds of nitrogen. The 3 pounds of nitrogen was probably okay, but 5 pounds it was fine throughout the year, and he didn't really need to apply too much more than that. Although the highest nitrogen fertilization level gave the highest quality in these evaluations, this amount of nitrogen is excessive for most golf courses in a cool, arid environment like northern Utah because of excessive growth in thatch production. So they say right there, the highest rate, although it was acceptable turfgrass quality, was generally not going to be recommended for various other reasons. The lowest nitrogen rate plots exhibited the longest ball roll compared to the highest nitrogen rate plot. So that's very common. We have a lot of growth, you have a lot of tissue, it's going to create more friction on the ball, it's going to slow the ball down. The lowest nitrogen rate, while fast, offered unacceptable visual quality, so a compromise between visual appearance and ball roll would be needed. Just basically what I'm saying. High rates of potassium did not reduce the need for nitrogen experiment 2, as indicated by the lack of N-K interaction on turfgrass quality. Opposite of these trends observed by Christians in 1997, tissue potassium was positively correlated with nitrogen fertilization rate from Nick's paper in 1977. I think I already went over that. And he even had a strong relationship than potassium fertilization rate. And that's what I did go over that. I remember the nitrogen actually had a bigger influence on potassium than potassium did. Okay. From the Christian's paper there, you can look back on that. I'll get into these potassium graphs in just a second. Oh, that was nitrogen. So that was the nitrogen papers, the nitrogen data. I'm not going to go into a whole lot of nitrogen. I think that's all I wanted to do on nitrogen. Now let's get into the potassium. Potassium is the nutrient usually needed in the second largest quantity by turfgrass. However, no positive effect of K fertilization rate was observed on turf quality. You know what? Let's pull this up. Hang on a second. I think I have it right here. Do I have this at the front of the paper? Oh, I don't. Let me see if I have it at the back. What did I do with that thing? Hang on a second. I'm going to open up this thing. Let me get to... I'm going to get to this. Oh, you know what I think I did? I think I might have deleted it on... Oh my goodness, I think I deleted it, but I can recreate it. I'm keeping a scoreboard on potassium papers. And I had it updated, and I think I deleted it because I had a duplicate. I think I messed up and deleted it on accident. Yeah, I did. I'll have to recreate it. Not a big deal. But what I was going to do is I'm going to put this paper in the no response column. So here's another paper. This is 3 now. Okay. And actually, I think I'm going to add in, I think later on we're going to see something else happen here, where it says no positive effect of K fertilization rate was observed on turf quality. None. No significant difference among K levels were observed in 2000 or 2001. Higher rates of K reduced quality in 1999, but this was due to foliar burn. So now here's another paper that goes in the no response column and into the negative column. I don't know why everybody applies so much potassium. It's absolute madness. It's most of the time nothing happens. Sometimes at certain times of the year with certain types of turfgrass, there may be a benefit. Many times there's a disadvantage, increases in certain diseases, potential for foliar burn. All these things can occur by applying potassium that you don't want. Okay, so it's just madness. The lack of response was unexpected, not by Dr. Shaddox, considering the very low levels of soil test potassium at the start of the experiment. Not by me. I would be shocked if you saw a positive response potassium. And I know of one case, and I'll show it, where there was a very clear positive response potassium. I know of 2 cases actually in warm season grasses. But those 2 cases, I know the researchers that did it, and I worked with them, and they intentionally lowered the potassium by flooding the grass, flooding the soil, and growing the grass and harvesting out the potassium before the study started to get the potassium levels low enough so that you could see a positive response to it. Okay. But I would be far more surprised to see a response than to not see a response to potassium. Okay. Even when she says here, the authors say here, not she, I think the first author is a male, considering the very low levels of soil test K at the start of the experiment, very low levels of potassium, and they still didn't see a response. Soil test potassium was increased slightly by potassium application rates, but not in proportion to the amount applied. Tissue K showed a weak positive correlation with turfgrass quality, very weak, and I'll show that. Tissue K negatively influenced ball roll distance, but a significant relationship was observed only in year 1. So let's look at ball roll, and let's look at I'm going to look at figure 7 and I'm going to show that in a second. Figure 7, figure 8. Okay, figure 8. Here we go. So figure 8 is the relationship between tissue potassium and, tissue K. Okay, tissue K and turfgrass quality. And just like in the Christian's paper, we're going to find the R squared. I think, it wasn't the Christian paper. It was the Johnson paper, I think. Had the R squared was 0.13. 0.13. So we have almost no ability to predict what's going to happen with turf quality just by looking at tissue K. Okay, even on this paper. And they showed a negative correlation, basically a harmful effect on ball roll as the potassium rate goes up. Now in 2008, we have an R squared of 0.08, not very good. But the slope was negative. In 1999, it was a 0.46, still not great. The R squared is still not great. It's a 0.46. Like I said, anything 0.6, 0.7 or greater, we can start having some confidence in. But, below that's like, too much variation we're not accounting for. But the R squared is 0.46, and it's still negative sloped. So I don't have a whole lot of confidence predicting what the ball roll will be based upon tissue K. But I am pretty confident that on this particular creeping bentgrass cultivar, with these tissue K levels, you're not going to see an increase in ball roll. You're not going to see it stay the same probably. You're probably going to experience a reduction in ball roll, a reduction in green speed by inflating the potassium in the tissue so high. Okay? But yet we keep putting it out. I don't know why. The lack of turfgrass response to potassium has been observed in other research and was explained by lack of stress on the turfgrass and inherently high amounts of potassium present in sands, which is mostly true. Potassium is known to increase tolerance to heat, drought, and traffic stress. And he cites Turner and Hummel and Carroll's. Now, these are books. This is one thing where I'm like, I wouldn't put much confidence in that, because if you read those books, they don't cite any hardcore evidence or published data on potassium. It says is known to increase. I would say potassium is claimed to increase or hypothesized to increase tolerance to heat, drought, and stress. Now, clearly, we've shown some issues with some benefits with winter kill. I haven't got into all the other stuff yet, but there's not a whole lot there when it comes to traffic stress. There's not a whole lot there. Okay, so I would, unfortunately, I'm questioning those two citations. There's not a lot in those citations that support that statement, but whatever. As she says, or they say, so future work should include the effects of traffic and water stress with K treatments, which I agree. I mean, there has been work done since then. Mean soil test potassium ranged from 28 to 46 parts per million. So that was the average. Now let's look at let me just go to the PowerPoint. Okay, let's go to the PowerPoint, and I'm going to, if I can get this on, I think I'm somehow messing this up. So just this first, and then go to PowerPoint. Okay, now let's go to the PowerPoint presentation. There's only 2 slides on this, guys. So, hang on, okay, sorry, I didn't have it set up. So, the PowerPoint, the first slide is the effect of soil sample depth on soil test potassium. We're going to see what happens when you apply 2 pounds of N and no K, 7 pounds of N and no K, 2 pounds of N and 8 pounds of K, or 7 pounds of N and 8 pounds of K at 0 to 3 inches, 3 to 6, 6 to 9, and 9 to 12 inches in soil in depth on Olsen soil potassium. And we see that the 0 to 3 is where most of the potassium is. Okay, right here, 0 to 3 is the blue bar. Let's say when you apply no potassium and 2 pounds of N, your parts per million of potassium in the top 3 inches is 36 parts per million. You go down just another 3 inches and it drops to 16. It drops by half. So if you're taking soil samples and you're not accounting for the depth, you're just taking them willy-nilly. If you take it to the top 3, you got twice as much as if you take it in the next 3 inches down. So when you sample, that's the reason we say you have to sample the same depth every time. Because if you take one sample at 3 and another sample at, say, 5 or 6 inches, you just diluted the sample down. It's probably, I guess theoretically, it'd be the average between 35 and 16. So it'd be your potassium would be 20, 22 parts per million on one sample. And the next sample you take at 3 inches is going to be 36 parts per million. Okay. When you're applying potassium in the top 3 inches is near 70 parts per million in the top 3 inches, where it's only 42 in the 3 to 6 inch depth. So if your probe goes down and hits this part and that's it, you're good. If that's, in terms of consistency. But if you're not consistent and your probe goes down a little deeper, you're going to dilute this 69. So if you've historically taken the samples, you're trying to take the samples at the same depth and you want to see the changes over time from some pre-existing condition, you could be greatly off simply because that soil probe went down to 4 inches or 5 inches or 6 inches rather than staying at 3 inches, or went down to 9 inches rather than 6 inches. You see a reduction here from 6 inches to 9 inches as well, from 42 at 6 inches to 29 at 9 inches. Okay. So for potassium, it's going to be diluted. It's going to be reduced the deeper you go. So if you have your probe and you weld on a piece on the probe at exactly the depth you want, which I would recommend 6 inches because most calibrations and correlations for soil tests have been conducted at 6 inches. So I'm relating the sample that I'm sending in to the numbers that are coming back. If I'm going to do that, the numbers that are coming back came at 6 inches more than likely. If that's true, then you need to sample at 6 inches. If the numbers coming back from the lab were say the calibration and correlation was done at, say, 3 inches, then you need to sample at 3 inches. How would you know that? You have to call a lab and ask them. And if they don't know, go to another lab. Go to the university lab, ask them. What sampling depth was used in the creation of this calibration and correlation on soil test? Because if their interpretation was conducted at 3 inches, they're going to have a much higher number than if you're sampling at 6 inches. And if they did it at 6 inches and you're sampling at 3 or 4 inches, you're going to have a much higher number than they did. Okay. So it all depends on how deep the sample was taken when the calibration and correlation was done. Regardless, if you want to stay consistent, you need to have something welded on the probe, or just go get a hose clamp, which is a little metal band with a screw on it, slide it over your probe, screw that down at the depth that you want. Okay. And the screw part is, it's like if you haven't seen it, it's a bolt or a screw. Turn that around on the back end of the probe so that it's extruding out from the back of the probe. Tighten it down tight. And then when you stick that down in there, the soil sample is going to stop at that hose clamp. Find something that stops the probe from going into the soil at the depth that you want. Okay. So that's the issue with soil sampling depth. Now let's look at what happens with seasonal changes. So Olsen extractable potassium, seasonal changes. Now we're looking at a graph here. The x-axis has April, May, June, July of 2009, all the way to October 2009, and then April through October 2000 and April through August of 2001. So these are the authors are sampling the soil every month or two from 1999 to 2001. And I'm going to show what the seasonal extractable soil test potassium is at 0 pounds a K, so no potassium was applied, or when 8 pounds of potassium was applied. And this graph is actually on their their paper. I just put it on this for my use later. And we see what happens if you don't apply any potassium. Now let's look at this. If you don't apply any potassium, the Olsen potassium started off around 22 or 3 parts per million in April, and then it goes up in May and June and goes back down until April 2000. Then in April 2000, they started applying potassium again, and it goes up. This was no potassium. Sorry, this was no potassium. There's no potassium being applied here. The potassium goes up from April to May to June to August to October, and then plummets down between November, December, January, February, March, and April, back down to about 15 parts per million. And then it goes back up April, May, June, and goes back up in August. So in other words, it's going up from April into the summer and then back down in the winter when no potassium was applied. How is this possible? How is potassium going up from April in Utah, going up in a putting green, maximizing its extractable phosphorus in, say, late summer, and then declining back down to its lowest level each year in April? Anybody want to venture a guess? That's what's happening. See if I can remove that. I can't remove that. So what I would postulate is likely the assuming that there's no error. I'm assuming they didn't dump potassium on the wrong plots. I mean, that, stuff can happen. But assuming that everything's equal, nothing wrong, nothing flawed happened. What I would argue is that there's potassium-bearing minerals in that soil, in that sand. And as the summer continues and it gets hotter and hotter and hotter, those potassium-bearing minerals are mineralizing some of that potassium throughout the summertime, reaching its zenith and its maximum, and then going back down into the cool temperatures through December, January, February, March. And then in April is its lowest point, and then the temperature goes back up, and more potassium is being mineralized, and then it goes back down. Okay? So, what do you do in this case when you have someone telling you you should sample 3 times a year? Keep in mind, there was 0 positive response to potassium in this study. There was only a negative response in ball roll. Okay? So the turfgrass didn't respond to potassium. Let's look what happens with 8 pounds. It's similar trend with 8 pounds. It's a very similar movement where you go up in the summer, down in the winter, up in the summer, down in the winter for 3 years in a row. So we have to sample. So we come in here and sample in April and we go, oh my gosh, it's 30 parts per million. We got to apply some potassium. And then we apply some potassium and now we're at 60 parts per million. Well, if we didn't apply any, we'd be at 40 parts per million in June. So we sample again. We go, oh, we got 60 parts per million potassium. So whether they say that's good or not, I don't know. Oh, we're good. We don't need to apply any more potassium. And then you go back down into April and you sample again. Oh, we're low. We're back down to 30. We got to apply more potassium. And you're on this constant roller coaster of chasing numbers on a soil test. And it only becomes exacerbated because, according to the USGA green section, you're doing it 3 times a year now. It's bad enough doing it once a year. Okay? When you don't have any problems. I mean, if you have problems, you have a pre-existing condition, that's different. But if you don't have any problems, sampling once a year, chasing numbers, you're chasing that roller coaster up and down. This is literally, not even metaphorically, this is literally a roller coaster. Okay? This is a roller coaster of potassium, whether you applied potassium or you didn't apply potassium. Look what happens in October 2000. When you did not apply any potassium, it's actually greater than if you applied 8 pounds of potassium on the soil test extract. Okay? It's 60 parts per million versus, say, 50 parts per million. If you applied none versus if you applied 8 pounds. So we're in here sampling throughout the year 3 times. And we see it's low, we're going to apply some. Or see it's higher, we're not going to apply some. We're going to see it's low, we're going to apply some. Meanwhile, this fluctuation is occurring when no potassium is being applied. Okay, it's none. There's none being applied here in the blue line. And it's still going up and down. And across all of these samples, across all of this entire line, the blue line, the red line, 0 pounds of K, 8 pounds of K, across all of it, the turf never showed a beneficial response. None. So if you take 20 and go, oh, we got to apply some, the turf was fine. The turf did not respond to applying potassium. You didn't need to apply any potassium, but you still applied some. And now you're up here at high. Oh, we don't need to apply any. You didn't need to apply any to begin with. But now you're in this cycle of applying more and applying. No, don't need to apply some. We need to apply some. It's we're low. We need to apply some. We're high. We don't need to apply some. You're constantly chasing your tail. And the whole time, no response to potassium ever occurred. No positive, no beneficial response to potassium ever occurred. That's my concern when we start talking about soil testing annually. And that gets magnified exponentially, my concern, when you have someone saying you need a soil sample 3 times annually. Okay? It's just absolute madness. So let's go back to the PDF and we'll wrap this thing up. Potassium levels in the green changed throughout the year. Levels generally started low in the spring and increased throughout the year, even with no potassium. The low levels of potassium early in the spring provided further evidence for leaching of potassium over winter. So they didn't measure leaching, so they don't know. But very likely that potassium in a sand base, once it mineralized, let's say it did mineralize from a potassium feldspar or something, it's not going to hang out in a sand base green. It's going to be moved through probably with the wetting front. The cause of the gradual increase throughout the year in control plots is unknown. Yeah, they don't know. That's true. Potassium is not being supplied from the irrigation water. They measured that. There was no potassium in the irrigation water. This increase may be caused by the occasional deposition of clippings from adjacent plots, which, again, that's an error in terms of the methodology, but it happens sometimes. Clippings from adjacent fertilized plots or the release of potassium during mineral weathering. And that's what I mentioned. There's very likely a human factor in here. If they had clippings go from one plot to the next, it's very possible that could occur if they didn't account for that. But if the soil contained potassium-bearing minerals, that would also explain that increase in potassium throughout the year. The lack of positive quality response and low soil test response to potassium suggests that careful potassium management is needed on sand root zone putting greens. Unlike in finer textured soils, potassium cannot be banked or applied in excess of plant needs in 1 year. Instead, on calcareous sand greens, potassium must be applied or made available to plants on a regular basis to maintain adequate tissue levels. I'm not concerned about tissue levels per se, but their point's well made. So in summation, the conclusions of the study were this. Potassium didn't provide any beneficial response. It actually had a negative correlation to ball roll, or reduced ball roll. The potassium in the soil test changed as the depth of the soil probe went down. So we need to maintain a consistent depth on a soil probe. I can't stress that enough. If there's one thing I would tell people, I don't do any soil tests. I don't see the point in doing soil tests on my own lawn. My turf's fine. But if for some reason I did, I can't stress enough the importance of finding some mechanism on that probe to make it stop at the same depth every time. That is the number one source of error in soil testing, in my opinion. And you can control it. It's in your control. It's not in the lab's control. It's not in the scientist's control. You have to control that. Okay? So please do that. The soil sampling, the soil extractant of potassium changed over in depth. The soil potassium changed throughout the season. It went up throughout the summer and down in the winter, up in the summer and down in the winter. Okay? The phosphorus levels were, for the phosphorus levels appropriate or needed for adequate turfgrass was 3 or 4 parts per million Olsen. Very low. Anything greater than that did not result in a concomitant increase in quality at all. It was a plateau. So those are the conclusions. Wasn't much phosphorus needed. Wasn't much potassium needed at all. There was no response to potassium. Okay. And the response, the turfgrass was deficient in phosphorus in the beginning. They mentioned it was weak in purple color, and it responded very quickly. Okay? If there's any questions, you better put it in the chat now. That's all I got on that paper. I like that paper a lot. There's a couple, like I said at the beginning, there's a couple little quirks in it. I wish they would have added. I wish that I would have known exactly what the quality limit was. They cited a couple of books rather than some papers, and those books I don't have a lot of confidence in those books. I would rather cite papers than books, because books are not edited or reviewed in the same with the same criticism as papers are. So I don't have as much confidence in books as I do in refereed papers. Okay, so Backyard Canuck. Morning, everyone. Sorry I'm late. Didn't get home from work until 4 a.m. Good grief. Where do you work, Backyard Canuck? Andrew Burris, is the nitrogen causing the increase? The increase in quality or growth? Yeah, nitrogen's causing it. Phosphorus did too a little bit, don't forget. It was deficient in phosphorus. And they did state that the 0.1 phosphorus was not enough. It was the 0.5 pounds of phosphorus that was needed to kind of get the turf out of that phosphorus deficiency. But nitrogen is driving the boat there, yeah. And Randy from Bulgaria, can you share pictures of my lawn? You want pictures of my lawn? I'll tell you what, I'll post pictures of my lawn on my YouTube channel. The members only stuff is going to be coming up in a month or two. And I've already actually posted some stuff on my YouTube channel, on the community section of my YouTube channel for members only, but there are no members. I haven't opened it up yet. So if you do choose to join as a member to the channel, you'll have access to whatever I've put on there. There's a couple of comments I've had about some fertilizer. I bought some fertilizer recently that was crazy expensive. I can't believe what homeowners will pay for this stuff. And so I'll put that on the YouTube channel comment section, Randy, if you want to see that, because some people want to see my lawn. Right now, my lawn doesn't look that good. There's a couple spots in there that I can't quite figure out from some old dead trees that have died. But yeah, I'll show my lawn if you want to. Backyard Canuck is a locomotive engineer. My grandfather worked on the Rock Island Railroad for decades, and it went bankrupt, I guess, back in the 70s or 80s. Okay, I'm going to let you guys go. I'll be back tomorrow. I have some music for you guys to listen to as we close up. If you have anything, let me know on an email. You can always go to calendly.com, TravisShaddox, if you want to have some consultation with me. Otherwise, I'll close it off for the day, and I'll see you tomorrow morning. Thanks, guys.